Okay, fine. Yeah, very good morning to all. And again, coming to the session two of operating system. Today, what we are going to be discussing is the computer system structures. So, before going to the detailed discussion about computer system structures, so first of all, let us will review what is we taught in the last class. So yesterday, what we have been seeing is that what is a computer system? What is the major components of a computer system? Various standard definitions of a computer system, and followed by what is the main goals of an operating system. Main goals of an operating system is that number one, convenience for the user. Number two, efficient operation. And followed by early systems we have been seeing. Early systems in a sense completely dedicated machines. Okay, in earlier days in 1970s before, whenever the user is trying to execute any particular program, what are the various actions which is going to be taken by your users and how they are going to be struggling for executing a particular program. And after that, they have been identified very important point is that the CPU is going to be sitting the most of the time idle during the transaction of loading and unloading the tapes. And after that, we have been gone for the next topic, resident monitoring systems, followed by overlap CPU and IO operations. Then finally, they have been concluded that we cannot catch up the speed of CPU. Okay, so we need to invent some software which must be responsible for keeping the CPU busy at all the times. So that they have been first introduced a term called it as operating system. Okay, the main purpose of operating system is that to keep the CPU busy at all the times. That is reason. And followed by we have been seeing various types of operating systems today that is available in the market. That is number one, the multi-programmed operating systems. Number two, time-sharing operating systems. These are all, and after followed by, we have been seen another two very important multi-processor organizations. One is parallel systems, and second one is a distributed system. And after that, we have been seen about real-time systems. What is real-time? These real-time operating systems are especially suited for embedded system software applications. This is what we have been seen at a glance in the last class. Now today we are going to be see the operating system structures. So in this particular topic, what we are going to learn is that okay, what are the various components which are involved in a computer system, how they are communicate with each and every other. Okay, so whenever the user has been switched on the computer system, what are the various action which is going to be taken by your computer system? Actually, really says that this topic is already you have been covered in computer organization. Okay, the same topic is also going to be repeated here. Why? Because we must know that what is the speed mismatch between CPU and memory? What is the speed mismatch between CPU and IO devices? In order to overcome all these physical difficulties, we have been entered into a new, maybe a technique call it as operating system. That is what is going to be called it as computer system structure. And followed by, we're going to be say a small discussion on okay, what is an interrupt? What are the different types of an interrupts? So whenever a IO device want to communicate with the CPU, how it is going to be possible? This is we're going to be see. And the last but not the least of this topic is that what are the different kinds of memories available, and how whenever the user is trying to execute this program, okay, how your program is executed by distributing your program in various memories. We're going to see this particular topic. And the last one, caching, coherency, and consistency. These are the topics what we are going to see in this particular topic. Now we move on to the slide, first slide. Now, coming to the first one, computer system. As from yesterday discussion, you're already everyone aware that a computer system is majorly it is a collection of four components. Okay, number one is hardware. Number two, operating system. Number three, application programs. Number four, users. This is yesterday's discussion. Now we're going to see that, okay, what are the various components are there in a computer system, how they are going to be interconnected with each and every other. Okay, now coming to the first very important component in a computer system is CPU, and the second very important component is memory, and the third very important component is a list of IO devices. Okay, now coming to the first one, okay, these all devices are going to be okay connected through some dash lines I have been showing with the bar. Okay, and this is going to be called it as bus. This is going to be called it as bus. Okay, now what is bus? A bus and the CPU, memory, and IO devices all are going to be connected through a bus. What is a bus? Okay, non-technically we can define it as what is a bus in the sense a bus is a collection of wires which can be used to exchange the information between any two peripherals. Okay, a bus is a collection of wires which can be used to exchange the data between any two peripherals. Now, so technically now we're coming to the bus. What is a bus? A bus is a collection of three components. Number one, address bus. Number two, data bus. And number three, control bus. Coming to the first one, address bus. Address bus simply specifies the address of the address bus simply specifies address of specific memory location where the address of either specific memory location or IO device where the operation is going to be carried out. This particular bus is a collection of three components. Number one, address bus. Number two, data bus. And third one is control bus. Address bus simply specifies the address of specific memory location where the operation is going to be carried out. The different kinds of operations you are going to be carried out is either read or write that is specified by using control bus. And the third one is data bus. Data bus is used to exchange the data between any two devices, either CPU to memory, memory to CPU, CPU to IO device to CPU. This is this one. Now, these all devices are connected through a bus. Now, every IO device is connected through a controller. What is this particular controller? Controller in the sense it is nothing but device driver, okay, which is nothing but a device driver. What is a device driver? A device driver is a small program which is responsible for the operations of the specific device. That implies that device driver program knows that how to control the status bits and flag bits of the entire device. Status bits and flag bits of the entire device. Suppose let us take an example. From a keyboard you are typed K. So through that particular communication media, you are not sending K, you are sending only signals. This signals is going to be converted into a machine language, and machine language internally converted into human readable format, and it is going to be displayed on the monitor. Who is going to do all this particular task? It is going to be done by your device driver. So what is a device driver in a sense? A device driver is a small program which knows that how to control the status and flag bits of the specific device. Simply says that the complete operations is going to be known by only controller. That's why before okay, using any particular device on your computer system, first of all, we must have a device drivers of the specific device should be known to your operating system. Otherwise, the device will not going to work at all. That's it. And similarly, memory controller is also there. Same. These are device drivers. So now the CPU, memory, and IO devices, they all are going to be connected through a bus. Now, so this is a bus can be used to connect between any peripherals and which can be used for exchanging the data between any two devices. Now, so whenever the user has been switch on the system, so what are the various operations which is going to be done by your computer system? Okay, whenever the user has been switch on the computer system, first of all, okay, post will going to be happen. What is post? Power on self-test. What is power on self-test in the sense? What are the different kinds of peripherals which are connected to your computer system? Whether each and every peripheral is receiving a proper power supply or not. Whether each and every peripheral is receiving a proper power supply or not. That is the first very important whenever the user has been switched on a computer system. You can observe it. When you switch on the system, all the lights, the CPU light, keyboard light, mouse light, everything is going to be first of all set it on and checks that whether each and every peripheral, whatever it is connected to your computer system, okay, whether each and everyone is properly receiving a power supply or not. Once power on self test is done, the second very important process is that booting. What do you mean by booting? Booting is nothing but loading the operating system into main memory. Booting is a process of loading the operating system into main memory. Who is responsible for loading the operating system into main memory? Okay, who is responsible for loading the operating system into main memory, which is done by bootstrap loader. What is this bootstrap loader? Already you know that from the last class discussion, a loader is a program which takes our machine language programs as an input and loads that particular program into main memory and preparing for execution. That is setting the starting address of the program to program counter for initiation of execution. Now, this bootstrap loader program is going to resides on zero track of your hard disk. This bootstrap loader program resides on zero track of your hard disk. Okay, then bootstrap loader is also a program. So whenever according to the basic principle, whenever the user is trying to execute any particular program, first of all, a program should be copied into main memory. Then bootstrap loader is also a program which is resides on zero track of your hard disk, who is going to be responsible for loading the particular program into main memory. So which is done by ROM BIOS routines, which is done by ROM BIOS routines. What is this ROM BIOS? Read only memory, basic input output system. So okay, now once power on self test is done, immediately the control is passed to ROM BIOS routines. This ROM BIOS routines internally contains a permanent programs which is responsible for how to load the bootstrap loader program into main memory. How to load the bootstrap loader program into main memory. Once ROM BIOS routine program has been run, it brings that bootstrap loader program into main memory. Once bootstrap loader program comes into main memory, then bootstrap loader program is run. It knows that how to load the operating system into memory. Once operating system has been properly loaded, now your system is ready for taking actions from the user. This is what is whenever the user has been switched on a computer system. These are the various actions which is going to be taken by your computer system. Number one, power on self test, that which and every peripheral is properly receiving a power supply or not. And after that, immediately the control is passed to ROM BIOS routines, which is internally loads the bootstrap loader program. This bootstrap loader program, by running this bootstrap loader program, it knows that how to load the operating system into main memory. That's it. Now, now, so how a CPU will going to be receiving an actions from any particular IO devices? The CPU will going to be receiving an actions, or you may call it as an occurrence of an event of a CPU is always by means of an interrupt. So what is an interrupt? And in case if any IO device want to communicate with the CPU, either it may be a desk or it may be a keyboard or mouse or printer or it may be a monitor, anything. If they want to exchange any kind of information with CPU, they want to give any instruction to the CPU, that is always possible by using interrupt. So what is an interrupt? An interrupt is a signal which is received by the microprocessor, or may call it as CPU, indicating that one external IO device want to communicate with CPU. A CPU is okay. What is an interrupt? An interrupt is simply defined as it is a signal received by the CPU indicating that one external IO device want to communicate with CPU. That implies in case if any IO device want to exchange any kind of information with the CPU, that is possible by using only interrupt. Okay, so now coming to the first one. Suppose let us take an example. So in order to get a better understanding of a student, now I'll give you a small example. Suppose I am teaching a class. Some student is came in front of me. They want to talk with me. Then simply he calls me, sir. What is the meaning of that? Why he has been called sir? In the sense he is an interrupt. Why he has been given an interrupt to me? He want to exchange a piece of information with me. That's why he have been given an interrupt. That is called it as an interrupt. An interrupt is a signal which is received by the microprocessor indicating that one external IO device want to communicate with the CPU. That implies Now, how these interrupts are going to be internally classified? There are several classifications are there. Coming to the first kind of classification is the maskable and non-maskable classification of interrupts. Okay. Maskable in the sense, such kind of an interrupts can be ignored by the processor. It cannot cause any problem to the CPU. But whereas in the case of a non-maskable interrupt, the CPU has to be immediately responded. Such kind of an interrupt. This is the first kind of classification. Maskable and non-maskable classification. A maskable interrupt can be ignored by the processor. It does not cause any problem to the CPU. But whereas in the case of a non-maskable interrupt, the CPU has to be immediately respond to such kind of a interrupt. That is first one. Let us take while I am teaching this particular class, one student is came in front, he asked, okay, sir, but I didn't, okay, bothered about that particular sir. Then I continued the class. Such kind of an interrupt is going to be called as maskable interrupt. I cannot going to be bothered. Suppose if another teacher came and he called me, sir, then what I need to do? Immediately I need to stop here, I need to respond it. That is non-maskable interrupt. I need to immediately respond to it. Such kind of, that is the first kind of a classification, maskable and non-maskable classification. And coming to the second very important classification is that software and hardware interrupts. And the second one is software and hardware interrupt. While executing a software program, it is unable to compute whatever the operation which has been specified. Then at the moment, whatever the interrupt which has been generated, such kind of an interrupt is going to be called as hardware interrupt. Sorry. Okay. So while executing a software program, it is unable to continue whatever the operation which has been specified, then it is called as software interrupt. Let us take an example. You have been written a program. In that particular program, you have been written one line, C is equal to A by B. In that, B value is equal to 0. What happens? If B value is equal to 0, you may get an error, call it as a division by 0. Then such kind of errors are going to be called as software interrupts. Such kind of an interrupts is going to be called as software interrupt. Let us take now another example. Okay, hardware interrupt. While executing the operations in the hardware, if the hardware is unable to continue the operation whatever it has been specified, so that kind of an interrupt is going to be called as hardware interrupt. Okay, now what is this one? Let us take an example. Suppose you have been given, okay, you have been given print. So you have been asked you to print 10 pages of printout, but the printer is accumulated with only 8 pages are there. After printing 8 pages, it unable to continue the operation. Then immediately it generates an interrupt to the CPU. Whatever the task you have been specified to me, I am unable to continue it. Why? Because there is no papers are there. Then immediately it gives an interrupt CPU. Then immediately CPU delivers a message on a monitor, paper feed error. That is going to be called as hardware interrupt. This is second classification. First classification is maskable and non-maskable classification, and second classification is software and hardware. And coming to another one, in Unix point of view, we can call this interrupts as single device, single level, single device, multiple level, multiple device, multiple level interrupts. Okay, such kind of a discussion is separate, which is going to be you can completely learn in Unix. This one. Now we're going to be see that. Now, correspondingly, that is first of all what is an interrupt and what is the types of an interrupt. Now, so whenever an interrupt has been came to the CPU, how the CPU will going to respond it. So while executing, so this particular interrupts now, whenever a CPU has been received an interrupt, at the time the CPU is busy with executing some another program. So while executing one program, if the CPU has been received an interrupt from any kind of an IO device, what CPU is going to be doing? Now, this can be treated as two types. Number one, while executing a high priority process, a low priority interrupt has been encountered. Low priority interrupt has been encountered. What the CPU will going to be do? While executing a high priority process, they have been received a low priority interrupt. Then what CPU is going to be do? While executing one process, whenever the CPU has been received an interrupt, immediately the control is going to be passed to interrupt vector table. The interrupt vector table simply determines who is having high priority. Is having high priority while executing one particular process. In case if any IO device is generated interrupt to the CPU immediately control is shifted to interrupt vector table and determines the priority. But what is the priority of currently executing process? What is the priority of current received interrupt? Okay, suppose let's take an example. Case one: if currently executed process is having high priority and interrupt is low priority process, then what CPU will does is that CPU simply receive the request and put it in job queue, and CPU simply does the normal execution. That implies while executing a high priority process, whenever a low priority interrupt has been encountered, CPU simply put the job in ready queue and CPU does the normal execution. But whereas in case 2, while executing a low priority process, whenever a high priority interrupt has been encountered, whenever a high priority interrupt has been encountered, okay, then immediately CPU, okay, then identify that, oh, currently one is low priority. It need to stop the current execution and giving the control to high priority process. But before preempting the low priority process, first of all, you need to say the status of the current low priority process, where it has been stopped somewhere in the stack, and control is given to high priority process. Once high priority process has been completed, again the control is returned back to low priority process. Who is going to do all this particular task? Which is going to be done by interrupt specific handler. Which is going to be done by interrupt specific handler. Okay, so this is responsible for saving and restoring the status of processes while handling interrupts. Now, coming to the next very important thing is that whenever a CPU has been received multiple interrupts at the same time, whenever a CPU has been received multiple interrupts at the same time, how can the CPU can decide that which interrupt has to be serviced first? Okay, okay. Now your CPU can having a capability of servicing only one interrupt at a time. Okay, whenever the CPU has been received a multiple interrupt at the same time, okay, then CPU immediately, okay, determines who is having high priority. The high priority is always going to be serviced first. Okay, this kind of a concept is going to be called as handling multiple interrupts. So whenever the CPU has been received a multiple interrupt, which interrupt has to be serviced first? Which interrupt has to be serviced first? Now we're going to see how it is going to be done. Okay, in order to handle this kind of situation, we have two methods. Number one is going to be called as when handling two kinds of methods. Number one is going to be called as pooling method. Number two is going to be called as parallel priority interrupt logic. We have two methods. Pooling method, which is purely a software approach. Pooling method, which is purely a software approach. That implies it is a simple software program. You know that everyone can write a small program how to pick up the largest number from a given pool of numbers. It is a very small logic. Okay. So immediately once a multiple interrupt has been received, the CPU immediately determines the priority from interrupt vector table. Okay, and by using the software program, it determines that who is having high priority. The high priority interrupt is always serviced first. Good. This is a very good program. Why? Because okay, implementation is very easy. And the second one, if the number of interrupts is 10, same program itself is sufficient. If the number of interrupts is 20, the same program is sufficient. And that implies the in case if any modifications, if any new devices are added, no need to change this particular software program. This software program is working for any number of devices. That is this one. But the only one disadvantage with pooling method is that okay, it is very slow approach. You already know that from the previous class discussion, the time it will going to be taken for making one comparison. In that time, the CPU can having a capability of executing a millions of instructions. And now the CPU is going to be spending the most of the time for making comparisons. The CPU is spending the most of the time for making comparisons. This is in order to work in this particular problem. Next, they have been invented a new technique is going to be called as pooling method, which are parallel priority interrupt logic, which is also going to be called as hardware. Okay, hardware method. It is completely constructed by using hardware. So the main advantage of this particular technique is that it is very fast. Why? Because everything is in terms of signal processing. Everything is in terms of everything is in terms of signal processing. The only one disadvantage with hardware method is that okay, so in case if any modifications is there, the entire circuit has to be changed. This is what is going to be interrupts. Okay, what is an interrupt? An interrupt is a signal which is received by the CPU indicating that one external IO device want to communicate with the CPU. These interrupts are classified into two categories, maskable, non-maskable classification, software and hardware classification. Whenever the CPU has been received multiple interrupt at the same time, how can the CPU can decide that which interrupt has to be serviced first, which is going to be done by, okay, who is having high priority? The high priority interrupt is always serviced first, which is determined by using either software, that is a pooling method, or hardware method, which is also called as parallel priority interrupt logic. This one. And while switching from one process to another process, whenever an interrupt is encountered, we need to save the status of the current process where it has been stopped somewhere in the stack, and control is going to be switched to some another process. Okay, saving and restoring the status of a particular process is always going to be done. Saving and restoring the status of a particular process is always done by interrupt specific handler. That's it. This is the first topic what we are going to be seeing in computer system structure. So what are the various questions we have been played in earlier gate? So one in 1996, I hope. Okay, so we got, okay, whenever the user has been switched on, what are the sequence of actions? Number one, post. Number two, ROM BIOS. Number three, bootstrap loader. Number four, booting. What is answers? 1, 2, 3, 4. 4, 3, 2, 1. Something. 1, 2, 3, something. So answer is first power on self test, followed by ROM BIOS routines, followed by bootstrap loader, followed by booting. This is the sequence 1 need to answer. Now, and another question we have been got in 2 decades ago. We have, that is after 20 years before, we got one question. Division by zero error is comes in which category? Okay, whether it is a software interrupt or hardware interrupt. It is purely a software interrupt. These are the questions what you have been got. And another time we have been got another question. Okay. Question is that, so while executing a high priority, while executing a low priority process, whenever a high priority interrupt is encountered, so the saving and restoring the status of a process is going to be done by whom? Okay, and A, interrupt vector table, B, interrupt specific handler, C, something, D, something. Answer is interrupt specific handler. So this is the questions what we have been got in earlier gate. Now we'll move on to the second topic of discussion, is that the method of interconnection between CPU, memory, and I/O devices. First of all, we'll see the method of interconnection between CPU, memory, and I/O devices. And once you have been seeing this particular topic, next we have to move on to how the communication is going to be happen. How the communication is going to be happen between CPU, memory, and I/O devices. So coming to the first very important one is that the method of interconnection between. Okay, the method of interconnection between, okay, between CPU, memory, and I/O, and data transfer between CPU, memory, and I/O can be done by using the following 3 modes. Number 1, program control data transfer. Number 2, interrupt initial data transfer. Number 3, DMA transfer. So coming to the first very important one is program control data transfer. Okay, and before going to the technical discussion about program control data transfer, first of all, we'll see how these particular components are interconnected with each and every other. Okay, you're already aware of that. Every computer system is basically constructed with 3 components. Number 1 is CPU, second one is memory, and third one is I/O devices. And coming to the first one, CPU, memory, and I/O. These 3 units are connected by using 2 buses. These 3 units are connected by using 2 buses. One is going to be called it as memory bus, and second one is going to be called it as I/O bus. First one is memory bus, and second one is I/O bus. Okay, what is a bus? Already, okay, from the previous topic discussion, you already know that what is a bus. Non-technically, we can define it as a bus is a collection of wires which can be used to exchange the data between any 2 peripherals. So technically, we come to the bus. What is a bus? A bus is a collection of 3 components: address bus, data bus, and control bus. Now we'll see one. So coming to the first one, I/O bus. What is this I/O bus? I/O bus is a collection of 3 components. Number 1, device address bus. Number 2, data bus. Number 3, control bus. Device address bus simply specifies the address of specific I/O device where the operation is going to be carried out. What are the different kinds of operations you are going to be carried out is either read or write, which specified by using control bus. And data bus is used to exchange the data between CPU to IO and IO device to CPU. Let us take an example. Your computer system is equipped with several kinds of IO devices. Each IO device is having a specific address. Keyboard is having one address, mouse is having one address, okay, your hard disk is having one address, every peripheral is having one address. Okay, the operating system, okay, your CPU is going to identify each and every IO device by using this address. Okay, so a simple example is that in a class, every student is identified by a teacher by using a roll number. Yes, that implies a roll number can be used as a primary key to identify each and every student in a class. In a similar manner, an address of device address is going to be uniquely identifying each and every IO device. So IO bus is a collection of three components. What is that? At device address bus, number two data bus, third one is control bus. Device address bus simply specifies address of specific device where the operation is going to be carried out. The different kinds of operations are going to be carried out is either read or write, that is specified by using control bus. And data bus is used to exchange the data between CPU to IO device to CPU. And coming to the second very important one is memory bus. A memory bus is also a collection of three components. Number one, memory address bus. Number two, data bus. And third one is control bus. Memory address bus simply specifies the address of specific memory location where the operation is going to be carried out. Memory address bus simply specifies the address of specific memory location where the operation is going to be carried out. The different kinds of operations carried out is either read or write from is going to be called as specified by using control bus. That is, you can read the values from the memory or you can write the values onto the memory. That is specified by using control bus. You can read the value from a keyboard or you can write the value onto the monitor. That is specified by using control bus. You can read the data from hard disk. You can write the data on the hard disk. The read write is specified by using control bus. And finally, the data bus is used to exchange the data between memory to CPU, CPU to memory. That's why I have been defined as what is a bus. A bus is a collection of three components. Number one, address bus. Number two, data bus. Number three, control bus. Address bus simply specify address of specific memory location or IO device where the operation is going to be carried out. The different kinds of operations carried out is either memory read, memory write, or IO read, IO write is specified by using control bus. And data bus is used to exchange the data between CPU to memory, memory to CPU, CPU to IO device to CPU. That's it. This is what is happening. So now we'll see how communication is going to be happening. So everyone aware with C language. Okay, I hope everyone knows that C language basics. Now let us take an example. Scanf %d %a. So I have been written one program. Okay, while running one program, I got one statement, call it as scanf %d %a. I got one statement, call it as scanf %d %a. What is the meaning of this statement? The meaning of this particular statement is that you have to read one value from the keyboard. The value is of type integer. The value has to be stored in a memory location A. The meaning of this line is that you have to read one value from the keyboard. Please try to concentrate on this. Please try to read one value from the keyboard. The value is of type integer. The value has to be stored in a memory location A. Whenever the statement has been encountered, then immediately what the CPU is going to be does is that, first of all, the address of the keyboard is specified in device address bus. The address of the keyboard is specified in device address bus, and through control bus it initiates a read signal. Through control bus it initiates a read signal. Once this particular signal is received by IO interface, CPU does not execute any further instructions. CPU simply sitting idle until this read operation is finished. Then once this particular signal is received by IO interface, then what IO interface is done is that it immediately turns busy flip-flop on. It immediately turns the busy flip-flop on. Once the busy flip-flop is on, then the data is entered by the user from the keyboard, which is going to be taken and it is placed on data register. It is going to be placed on the data register. After placing the data on data register, then data ready flip-flop is going to be set it on. The data ready flip-flop is going to be set it on. Okay. Now the data another will take non. Now what is this CR? Now we'll see. This is called it as count register. What is this one? Suppose you have been written a statement scanf %d ampersand a ampersand b. The meaning of this line is that you have to read two values from the keyword. The first value is both are of type integer. First value has to be stored in a, second value has to be stored in b. So you need to read two values. That in that case you have count is equal to 2. After reading one value, count becomes 1. After reading another value, count value becomes 0. Once counter value becomes 0, then data ready flip-flop is on. In this particular case, scanf %c ampersand a, initially counter value is 1. After reading one value, the counter value becomes 0. Once counter value becomes 0, then the data ready flip-flop is set it on. Once data ready flip-flop set on, then CPU understood that, oh, whatever the data have been specified to read from the keyboard, from an IO interface, it is ready. Now I'll go and take that one. Then immediately what CPU does is that the data value is going to be placed on databus and it is going to be received by CPU and it is stored on internal registers of the CPU. You know what is internal register? A CPU is a collection of 3 components. A CPU is a collection of how many components? 3 components. Arithmetic logic unit, and the control unit, and third one is memory unit. Okay. So in memory unit, it will going to be stored that particular value of A. Now, so the value has to be stored in memory location A. Now CPU will going to be so address of A is going to be placed on memory address bus, and the data is going to be placed on data bus. And through control bus, it initiates a write signal. Once it is initiated, the value is going to be kept it on a memory location. The value is going to be kept it on a memory location, so which is already assigned to A. That's it. This is how it is going to be happen. Okay. This is how it is going to be happen. This is going to be called it as program control data transfer. Why it is named as program control data transfer, we'll see. Now, this is how it is going to be done. Now, coming to the one. So, first of all, whenever you have been got scanf %d ampersand a, first of all, IO read has been done, followed by memory write has been done. Suppose let us take another example. Printf %d ampersand a, printf %d %d a. So, what is the meaning of this? You please try to print one value. The value is of type integer. The value is stored in a memory location A. Whenever the statement is encountered, what happens is that, first of all, CPU, I place the address of A in memory address bus, and through control bus, it initiates a read signal. Then the data is read from memory and it is going to be placed on data bus and it is received by CPU. Then what receives the CPU? After receiving it, the CPU specify address of monitor. Why? Because I need to print this value on the monitor. So address of monitor is specified on device address bus and data is going to be placed on data bus, and through control bus I initiate write. Then the value is going to be written on the monitor. In this particular one, okay, operations is first of all memory read followed by IO write. This is what is going to be done. Now coming to the next one. Sir, why it is going to be named as program control data transfer? Suppose you have written one program. While executing that particular program, you got a statement scanf. Once a scanf is encountered, CPU simply blocks the execution until the data ready flip-flop is set on. Yes or no? Okay, your program execution is stopped until data ready flip-flop is set on. And that implies normally the CPU has to be control the program execution. But in this situation, what happens is that your program is controlling the execution behavior of the CPU. That implies by scanf instruction, it simply blocks the CPU execution until the data ready flip-flop is set on. Yes, that's why this particular kind of a data transfer is going to be called it as program control data transfer. Okay, why? Because your program is controlling the execution behavior of the CPU. Okay, that's why it is named as program. The main disadvantage of this particular method The main disadvantage of this particular method is that the CPU is going to be sitting idle until the data ready flip-flop is going to be sitting on. In order to overcome this particular problem, now they have been comes with a new technique is going to be called it as interrupt initiated data transfer. They have been invented. Listen, the earlier program control data transfer disadvantage is the CPU is sitting idle until the data ready flip on. In order to overcome this particular problem, then they have been comes with interrupt initiated data transfer. Already from the previous class discussion, you already know that what is multiprogramming. What is multiprogramming? So you already know what is multiprogramming. More than one program can be simultaneously reside in main memory. More than one program can be simultaneously reside in main memory. During the execution of one particular program, in case if any program requires an IO operation, the CPU does not sit idle. It simply switches from one particular job to another job. The CPU will not going to be sitting idle. It simply switches from one particular job to another job. Like this interleaved fashion of execution, giving a look and feel that all the jobs are going to be happening simultaneously. Then this kind of a concept is going to be called it as multiprogramming. So let us take, now an interrupt initiate data transfer is also the method of interconnection between CPU, memory and IO devices is done by using two buses. Number one is memory bus and second one is IO bus. Okay, which is a collection of three components: address bus, data bus, control bus. Address bus simply specifies address or specific type of memory location or IO device where the operation is going to be carried out. The different kinds of operations you are going to be carried out is either read or write, which is specified by using control bus. And data bus is used to exchange the data between memory to CPU, CPU to memory, CPU to IO device to CPU. The interconnection is same. Now, how it is going to be? Suppose let us assume there is three programs are already there in memory. Let us assume multiprogramming. There are multiple programs that resides in memory. While executing one program, you got a statement for it as scanf %d %a. So that implies you have to read one value from the keyboard. The value is of type integer. The value has to be stored in a memory location A. Now, so whenever this statement has been encountered, what CPU will going to be does is that, number one, first of all, it has to be, the address of the keyboard is specified using device address bus, and through control bus, it initiates read signal. Once the signal is given to IO interface, DPU does not sitting idle. It simply saves the current status of the process somewhere in the stack and CPU switches to some another job. You understood? Now the CPU is not sitting idle. Whenever an IO operation is encountered, simply the task is assigned to IO interface and CPU is simply switched to another job. Once this request is received by IO interface, immediately it turns the busy flip-flop on. Immediately it turns the busy flip-flop on. Once the busy flip-flop is on, the data is going to be read from the user, that is from the keyboard, and it is placed on data register. And after that, immediately the total values has been taken from the user, then it is going to be counter value becomes 0. Once counter becomes 0, the data ready flip-flop is going to be set it on. Once the data ready flip-flop is set it on, then IO interface is giving an interrupt to the CPU. Already you know that what is an interrupt. Already you know that what is an interrupt. An interrupt is a signal which is received by the microprocessor indicating that one external IO device want to communicate with CPU. What is an interrupt? An interrupt is a signal received by CPU indicating that one external IO device want to exchange a piece of information with the CPU. Now, once this particular interrupt has been received by the CPU, at present the CPU is busy with executing another process. Now, already from the previous class discussion, you already know that the old stop to process always gets a first priority. Now, CPU does the non simply stop the present execution and giving the control of the CPU to old stopped process. Why? Because the old stopped process always gets a first priority. Why? Because the old stopped process always gets a first priority. Now, before switching from current process to old stopped process, again it has to save the status of the current process where it has been stopped somewhere in the stack, and CPU control has to be switched to the old one. So once again it has been switched, after switching it, the data is going to be taken from the data register through device data bus, and say it is stored in internal registers of the CPU. And after that, CPU will going to be specify the address of A on the address bus, and the data is placed on data bus, and through control bus it initiates write, then the data value is going to be done, write it in memory. Now here you please observe it, the data transfer is initiated only when the interrupt comes from an IO device. This point is clear, everyone? Okay, the data transfer is initiated only when the interrupt is initiated from an IO device. And meanwhile, the CPU is going to be busy with another program. CPU is not sitting idle. Is it clear? That's why it is named as interrupt initiated data transfer. It is interrupt initiated and whenever an interrupt is initiated from an IO interface, an IO device, then only CPU is going to be takes the value. Okay, during that particular time. So during the reading the data from an IO device, CPU is not sitting idle, it simply executes some another program. Yes, that's it. Now, coming to the next one. So now, what is the main disadvantage of this particular one? Okay, the main disadvantage of this particular one is that, okay, saving and restoring the status of a particular process is not that much of easy process. It is very complicated. Saving and restoring the status of a particular process in the sense, so what you need to store? Currently, which program you are executing, which process you are executing, the process ID number, currently what is the program counter value, which variables it has been used, what memory locations has been assigned to them, what registers has been assigned to them. These all things has to be stored somewhere. This is not that much of easy process. It is somewhat complicated. It is somewhat, but this everything is under care of CPU. The CPU has to be does all this, but the CPU is becoming overwhelming for doing all this kind of tasks. Now, so this one. This is interrupt initiated data transfer. Now, so this is what we, in order to overcome program control data transfer in disadvantage, this has been invented. But another scientist has been given a good solution for reducing the idleness of the CPU. That is, the programmer should have a good estimate of time where to place the read statement. The programmer should have a good estimate of time. This we got one question in GATE. The question. What is this one? Let us we'll see explanation. Then we'll see how the question is came in GATE. We'll see at a later stage. Now the programmer should have a good estimate of time where to place a read statement. That is a scanf in your point of view. Suppose you have written 100 lines of statement, 100 lines of program. In 10th line, you have written scanf %d A. But the A value is not used until 80th line, 80, until 80th line. But you have been taken that value at 10th line. So your CPU has to be keep track that value until 80th line. How burden it is for the CPU. That's why, again, suppose if you place that particular read statement at 80th time, CPU burden will going to be reduced. That's why in C language, you know that, okay, the variable declaration must be allowed immediately after the begin. In between the program, you are not allowed to declare any variables at all. If you want to declare it, again, you need to open a braces and you need to declare the variable immediately after the first process. You have open it, write a declaration statement. But the problem is that the scope is limited to the block in which it is declared, and the life is till the execution of the block is complete. And the life is till the execution of the block is complete. Okay, so now such kind of a restriction is removed in C++. In C++, a variable can be declared anywhere in the program just before its usage. In C++, a variable can be declared just before its usage. That's enough. But C, we are not having such kind of a feature. Now, how do you get a gate bit in 2001? I hope. So 2001. Okay, how to reduce the idleness of the CPU while exchanging the data, while communicating the data from I/O device to memory. Option number A, by introducing interrupt initiate data transfer. Option number B, the programmer should have a good estimate of time where to place the read statement. Option C, both A and B. D, none of the above. The answer is C, both A and B. So that is the reason why I have been taught at this particular topic. Is it clear? Now, already from the previous class discussion, you already know that every computer is having minimum 3 components. Sorry, every computer is having minimum 2 processors. Number one is CPU and second one is I/O processor. The I/O processor is now, I am going to call it as DMA. Why I have been call it as DMA, I'll tell you later on. Okay, every computer is equipped with minimum 2 processors. Number one is CPU and second one is I/O processor. Number one is CPU and second one is I/O processor. Okay, CPU is responsible for executing arithmetic and logical instructions, and I/O processor is responsible for input and output operations. I/O processor is responsible for input and output operations. Now we'll see the method of interconnection between CPU, memory, I/O devices, and I/O processor. How it is done? Same as usual. It is done by using 2 buses. First one is, this is I/O bus, and this is what I am showing the cursor. This is I/O bus, and this is memory bus. Coming to the first one, I/O bus. I/O bus is a collection of 3 components. Number one, device address bus. Number 2, data bus. And number 3, control bus. Device address bus simply specifies the address of specific I/O device where the operation is going to be carried out. And the different operations that are going to be carried out is either read or write, which is specified by using control bus. And data bus is, this is data bus, which is used to exchange the data between DMA to I/O, I/O to DMA. This is first one. And second one is going to be called it as memory bus. So memory bus is initially connected between CPU and memory. Memory bus is initially connected between memory and CPU. Memory bus is also a collection of 3 components: memory address bus, data bus, and control bus. Memory address bus simply specifies the address of specific memory location where the operation is going to be carried out. The different kinds of operations carried out is either read or write, which is specified by using control bus, and data bus is used to exchange the data between memory to CPU, CPU to memory. The same bus is also used to connect between CPU to DMA. The same bus is also connected between DMA to memory also. Now, one bus is going to be shared between CPU, DM, I/O processor, and memory. Now, how communication is going to happen in this? Now, so let us take, according to multiprogramming, more than one program is simultaneously reside in main memory. More than one program is simultaneously reside in main memory during the execution of one program. In case if any program requires an I/O operation, CPU does not sit any idle. Now coming to the first one, while executing first program, CPU got scanf %d ampersand a, one line. Then immediately CPU does that. CPU simply specifies CPU simply gives an instruction to the I/O processor. You please try to get one value from the keyboard. And once this instruction has been issued to DMA interface or I/O processor, CPU does not play any role in the data transfer. Simply it saves the status of the current process and simply switches to some another process. Simply switches to some another process. Once this instruction is received by I/O processor, it enables address of the keyboard through device address bus, and through data bus it initiates a read signal. Once this particular signal has been received, busy flip-flop is turned on. After busy flip-flop is turned on, the data is read and it is placed on data register. And then after that, count value becomes 0. Once counter value becomes 0, the data in data ready flip-flop is set it on. Once the data ready flip-flop is set on, then the data value is placed on databus and it's applied to DMA. Then DMA gives an interrupt to CPU. Then DMA gives an interrupt to the CPU. Then DMA gives an interrupt to the CPU. Okay, whatever the value you have been specified to read from the keyboard, which is already done, come and take. And CPU simply says that there is, okay, why you need to give this value to me? There is no need of giving this value to me. You can directly keep this particular value in memory. Then immediately IO process says that how can I place this IO value into memory? Why? Because the memory bus is connected between CPU and memory. I cannot directly place the value in memory. Can you grant the bus, memory bus, to me to transfer the data into memory? Then CPU temporarily releases its memory bus to your DMA. That is IO processor. The CPU temporarily releases memory bus. CPU temporarily releases okay. That is called as cycle stealing. CPU temporarily releases its memory bus to IO processor to transfer the data. This kind of a process is known as cycle stealing. So once a bus is granted to IDMA, immediately address of the memory location A is specified in address bus. Data is placed on data register, and through control bus it specifies write. Then the value is going to be written on memory. That's it. So during the data transfer from IO device to memory, the processor participation is 100% eliminated during the data transfer. Okay, during the data transfer between IO interface to memory, during IO device to memory, the processor participation is 100% eliminated, except bus granting. Remaining the data transfer from IO device to memory, the CPU participation is 100% eliminated. Okay, now your IO processor directly placing the values onto memory, our IO processor directly taking the values from the memory. That implies your IO processor can having a capability of directly reading or writing the values from the memory. That's why it is renamed as, instead of IO processor, it is renamed as DMA, direct memory access transfer. Direct memory, and that implies your IO processor is having a capability of transferring data from IO device, okay, directly transferring the data into memory and directly reading the data from the memory. That's it. This is now today. So today every computer is having minimum two processors. One is the CPU and second one is IO processor. So you can also call it as DMA. That's it. So now how you get this particular question in okay, in 1 year gate we'll get this particular question as in which method of data transfer where the processor participation is 100% eliminated during IO to memory. A. Program control data transfer. B. Interrupt initiate data transfer. C. DMA transfer. D. None of the above. So answer is DMA transfer C. This is what question we have been already got in gate. Now we are moving on to the next one. Storage structure, or you may call it as hierarchy, storage hierarchy, or may call it as storage structure. Okay. Now, what is this? What are the different kinds of memories which are available? What are the different kinds of memories which is available in the sense? There are basically the total memories, whatever it is there in your computer system. These all memories are classified into 4 categories. Number 1, registers. Number 2, cache memory. Number 3, main memory. Number 4, all secondary storage devices. Number 4 is secondary storage devices. Okay. Okay. Now, these are the four types of memories which is available in your computer system. Coming to the first one, registers. What is this for the registers? See, registers are going to be inside the CPU. Okay, you know that what is a CPU? A CPU is a collection of three components: arithmetic logic unit, control unit, and memory unit. A memory unit, in the sense, it is a collection of registers. So this is the first one, registers, which is the fastest memory in your computer system. Which is the fastest memory in your computer system. And coming to the second very important one is that cache memory. It is the second fastest memory in your computer system. It is second fastest memory in your computer system. Okay. Now, coming to the third one is going to be called it as main memory. Third one is going to be called it as main memory. You may call it as RAM. And this is the third one. And coming to the last one is going to be called as secondary storage devices. That is hard disk, floppy drive, disk drums, okay, tapes. These are all comes under the category of secondary storage devices. From the diagram itself, you can understood that the registers are having with the less capacity, and rather than one. What is meant by capacity? In your computer system, first of all, we have been already talked about speed. The first place goes to register, second place cache memory, third one is main memory, and fourth one is secondary storage devices. Capacity point of view, cost point of view, the highest cost is a register. The second one is second place, somewhat cache memory, and third one is main memory, and fourth one is very cheap is your secondary storage devices. And coming to the third very important, capacity. In your computer system, maximum you can have 64 or 132 or 64 or maximum 128 register. Each register capacity may be either 32-bit or 64-bit. 64-bit. Okay, you can combine all this particular thing. The maximum capacity is in terms of only bytes only. And coming to the cache memory, today in market we have 512 MB, 512 KB, 1 MB cache or 4 MB cache, maximum in terms of kilobytes. And main memory is 512 MB RAM, 1 GB RAM, 4 GB. That is maximum in GB, kilo megabytes. And your hard disk is 500 GB, terabyte hard disk. These are all in terms of gigabytes. That's it. Now coming to this one, and the important this table shows that the memories are classified into four categories. Number one, registers. Number two, cache memory. Number three, main memory. Number four, secondary storage devices. Then speed point of view, the first place goes to fastest memory is register. Second place goes to cache. And third one is this one. And fourth one is secondary storage devices. So we got one question in GATE. Okay, among all these particular memories, which one is the fastest memory in your computer system? So most of the people written cache, but the answer is register. The fastest memory in your computer system is registers. Number one. Number two, the cost. The highest cost is register. The second one is somewhat cheap, cache memory. Some more cheap, main memory, and the cheapest device is secondary storage devices. The capacity is in secondary storage devices in terms of gigabytes, main memory is in terms of megabytes, cache memory in terms of kilobytes, and coming to the next one, registers is in terms of only bytes. Now you already know that, everyone. Okay, whenever the user is trying to execute any particular program, first of all, the program should be copied into main memory. So whenever the user is trying to execute any particular program, first of all, the program should be copied into main memory. Suppose if you want to run your program very fast, then what you need to do? You need to copy all the program in registers so that your program will going to work very fast. But problem is that your computer system is equipped with very low number of registers. The total amount of memory is in terms of bytes. That particular memory is not sufficient for running even hello welcome program in C language. Why? Because in C language you are writing a program called it as hash include std void main begin printf hello end. That's it. This is only one line of program I haven't written. In the first line, what I haven't written is that hash include. What is hash include? It is a pre-processor directive. It is a directive to the compiler. Before loading my program, first of all, transfer the contents of standard input output header file into memory. This particular file is there in secondary storage device and copy into memory. Your std avoided contains the thousands of lines of program. And that why? Because whatever the keywords have been written, pre-processor, before processing my program, first of all process the contents of standard input output header file. Why? Because whatever the keyword have been written, these all keywords meanings are just in standard input output header file. That is void, main, begin, printf, hello, printf, and these all keywords meanings are just in std. That's why before try to understand my program, first of all understand stdio.h. Okay, even that program is okay, that memory is not sufficient for running hello welcome. Now if you, okay, very cheap device, can you kept in secondary storage and run it? Okay, you can run it. It will take hours of time for running this program. This is too much of speed. Suppose you have a good amount of money for establishing a computer with all registers. You know what is the cost of a machine? Nearly it reaches to crores. At least 50 to 60 crores, 60 lakhs of money is required to completely construct with registers. It is working very fast. There is no problem, but it is not advisable. This is too much of slow. It takes hours of time. Then what you need to do? Whatever the amount of money you have in your hands, you please try to distribute your money among all these particular memories and try to see that your program is working more faster. Then what you need to do? Whatever the amount of money, okay, this is going to be called as the goal of memory hierarchy. The main goal of memory hierarchy is that we have to achieve the highest possible average access speed while minimizing the cost of memory systems. We have to achieve highest possible average access speed while minimizing the cost of memory system. And what you need to do? Whatever the money you have, so you please try to buy some registers, some cache memory, some main memory, and some secondary storage devices. Now, earlier I told one statement. Whenever the user is trying to execute any particular program, first of all, the program should be copied into main memory. Now I'm changing the particular statement. Your program is not only copied into memory. In order to improve the execution speed of your program, now I'm distributing my program among all these particular 4 memories. Among all these particular 4 memories. So what are the list of variables I have been declared inside? Okay, what are the list of variables I have been declared inside? These all variables are going to be, okay, placed in registers. And the second one, the program is consisting of a lot of control structures. That is loop control structures. That is CPU will going to be spending a lot of time for executing these loops. The loops are going to be placed on the second fastest memory, cache memory. And the normal instructions are going to be placed on main memory. If the main memory is also not sufficient for running your program, then I'll take a help of secondary storage. That is a separate topic. We'll see in memory management. That is virtual memory concept. Now, this one, by distributing variables. So whatever. So while executing each and every instruction, CPU repeatedly refers the values of variables. That's why I have been placed in registers. Loops. Loops in a sense, most of the time, CPU will going to be spending for executing this one. This also going to be called it as 90 to 10% rule. Suppose let us take an example. I have been given a task for 2 students for writing a small program. One guy written with 50 lines of code, another guy written with 100 lines of code. So among these 2 codes, 50 lines and 100 lines, which one is going to be executed faster? Most of the people says that 50 lines program is working more faster than 100 lines. Sorry, we cannot estimate the speed of an execution depending on the size of the program. So the speed of an execution depending on time complexity. Now that is not our topic. Now we'll talk about the speed of a particular program. Depends on the internal control structures, that is loops. Suppose If 50 lines guy has been written a program, inside one loop has been written for repeat 2000 times, then which program is working more faster? So that's why we cannot estimate the speed of an execution depending on the size of the program. So that's why it is going to be called as 90 to 10%. In order to execute 90% of the instructions, it will take only 10% of the total time. In order to execute only 10% of the instructions, it will take 90% of the total execution time. So this is going to be called as locality reference. Such kind of a locality reference loops or may call it as subroutines are going to be placed on cache memory. And coming to the third one, normal instructions are placed on main memory and remaining all instructions are placed in. By distributing this particular program like this, who is going to do this? This is all going to be done by memory management system, which is going to be done by memory management system. So memory management program is responsible for distributing your program among all these particular core memories and try to see that your program is working more faster. That's why it is going to be called as goal of memory hierarchy is defined as we have to achieve the highest possible average access speed while minimizing the total cost of the memory system. While minimizing the total cost of the memory system. While minimizing the total cost of the memory system. That's why now I am changing my statement. Whenever the user is trying to execute any particular program, the program is not only copied into main memory, the program is distributed among registers, cache, and main memory along with secondary storage devices also. By distributing the program among all these particular memories, the program execution speed is improved. That is called as memory hierarchy. We have to achieve the highest possible average access speed while minimizing the total cost of the memory system. And coming to the next very important small topic of discussion is that caching, coherency, and consistency. Okay. Now, what do you mean by cache memory? So, first of all, we'll see a small discussion on cache memory. Why? Because you may get questions in computer organization is also you're getting some questions on cache memory. How do you get that question? First of all, listen the topic, then I'll tell you how to do the problems. A cache memory is the second fastest memory. It is placed in between CPU and main memory. It is placed in between CPU and main memory. Whenever a CPU wants to read any particular thing, first of all, it checks that whether the value is there in cache memory or not. If the value is already there in cache memory, it simply gets it and executes it. If the value is not there, at the moment it goes to main memory. It brings a block of instruction containing that instruction. It simply brings a block of instruction containing that instruction and copied that instructions into cache memory. And from the cache memory only CPU will go in. CPU not directly read any value from main memory. CPU is always trying to read values from the cache memory itself. So whenever a CPU wants to read any particular value, first of all it checks that whether the value is available in cache memory or not. If the value is available in cache memory, it simply gets it and executes it. If the value is not available in cache memory, then it goes to main memory, brings a block of instructions containing that instruction, again copied that instructions into cache memory. From the cache memory, CPU will going to be read that. This is how it is going to be happen. How do you measure the performance of a cache memory? The performance of a cache memory is measured in terms of hit ratio. The hit ratio is simply defined as number of hits by number of hits plus number of misses. What is hit? Whenever a CPU wants to read any particular value, first of all it checks that the value is there in memory or not. In case it is there, it is called as hit. If the value is not there, then it is called as miss. Whenever a miss is encountered, you need to bring that particular values from main memory to cache memory. Now, you will get problems on access time. How do you get time? The access time of a hit is normal. The access time of a hit is equal to access time of cache, access time plus access time of main memory. You need to calculate. You definitely will get one question. Okay, calculate total access time for reading and Suppose you have totally 200 instructions. Among 200 instructions, 40 instructions are already there in cache memory, and 160 instructions are there in main memory. Okay. Now, what is the hit ratio, or may call it as what is the total access time for executing this program? You may get this kind of a question. It is a very simple formula. Okay, hit ratio is equal to number of hits by number of hits plus number of meshes. Now, coming to the next very important one is that coherency and consistency. From the previous class discussion, you already know that multiprocessor organization. What is multiprocessor in the sense? More than one CPU can be simultaneously reside in a same machine. They are close to communicate. In order to establish the communication between the processors, if they are using same clock pulses, same buses, same memory, then it is called as parallel system technology. In order to establish the communication between the processors, if they are using separate clock pulses, separate buses, separate memory, then it is called as distributed system. Now, either it may be a parallel or it may be a distributed system. What happens is that multiple CPUs are there, multiprocessor organization. Each and every processor is having separate cache memory. Each and every processor is having separate cache memory. So now, all are going to be sharing a common memory. This is, now I am assuming that it is a parallel system technology. Now, what happens is that, suppose A, some value is there. The value is going to be accessible by all these three processors, CPU 0, CPU 1, CPU 2. If you are not using any proper security mechanism for this particular value A, then A value is going to enter us into inconsistent state. The A value is going to be called as inconsistent. Let us take an example. A value is 5. Now CPU 1 want to add to that value, add to that X value, and CPU 2 want to add 3 to that value. Initially X value is 5. CPU 1 want to add to that number. CPU 2 want to add 3 to that number. Then what happens? After performing these two operations, the X value becomes 10. Why? Because 5 plus 2 plus 3, 10. But what happens? Suppose if X value is there, first of all, CPU 1 has been read. How it will read? First of all, it copies the X value into cache memory. The value is going to be written in cache memory. Then after that, CPU will read that particular value and make an updation on only cache memory. So before going to this discussion, inconsistency, first of all, we'll see if you remember it or I don't know. Writing into cache memory is two types: write through method, write back method. Write through in the sense, whenever cache value is updated, main memory value is also updated. Both are happening simultaneously. That is write through method. Write back method. The updation of main memory is postponed until their existence has been removed from the cache memory. Then it is going to be called as write back method. Then what happens now we'll see. So initially X value is 5. That is, X value is taken by CPU 1 and it is stored in cache memory as 5. And now it has been added 5 plus 2, 7. He didn't make any updation on main memory. So before updation, CPU 2 has been read the value. Now what is the main memory value is 5. Now it is goes to X value is 5. Now this guy adds 3. 5 plus 3, now it becomes 8. Now first he has been updated 7. And that he is overwrite. Then he is updated 8. Then what is the value answer here? 8. Suppose if this guy is first updated 8, and after that he is updated 7. In either of the cases, answer is either 7 or 8. But original answer is 10. Why this kind of inconsistency? This kind of a concept is going to be called as inconsistency. This kind of a concept is going to be called as inconsistency. Whenever a value is going to be shared by more than one CPU at the same time, if you are not using any proper security mechanism for that value, the data will going to be enters into inconsistent state. In order to work on this particular inconsistent state, then we'll go for coherency and consistency. What is this coherency and consistency? Whenever an updation has been done on one particular copy of cache memory, immediately that modification has to be done to remaining all the cases at the same time. Understood, everyone? Whenever an updation has been done on the cache memory of one particular processor, it is the responsibility of operating system to see that if the same copy is available in other caches, and try to see that modification should be happen in all the cases at the same time, in all the CPUs at the same time. Otherwise, inconsistent. That is qualified as, in case if the modification is happen in all cases at the same time, then it is qualified as consistency. If it does not happen like this, it is inconsistency. So now we'll take a live example for this. Now everyone aware of online reservations, railway reservations. So if online reservations, okay, and we can take general reservations, or you may take Tatkal reservations as an example. But everyone knows that Tatkal is the most familiar. Why? Because everyone is instantly planning their journey to move from one particular place to another place. In a Tatkal, okay, there is only 100 seats are available from the server. This is in memory. Now these 100 seats is accessed by multiple people at the same time. Whenever one reservation has been made by one particular person, the modification has to be reflected to remain other persons. If it is not like that, what happens is that one seat is going to reserved by multiple people. There is a lot of galata is going to happen on the trains. Then, so what happens? Okay, this is the first one. That's why. So let us you can trial it. You can log on to the Tatkal service. While you are logging on, the number of seats shown is only 200. While entering your name, it becomes as 180. After typing all your particulars, it becomes 20. After making payment, it becomes as 0. And after once your payment is done, your reservation is comes into waiting list. Why? Because that particular value is shared by all the people throughout India, throughout the world. And if any updation is done by one particular person, the updation has been done to reminding all the people at the same time. Otherwise, it is inconsistent. This is one of the famous application of this coherency and consistency. This is a discussion about this particular thing. And we'll got one question already. I told that which one is the fastest memory in our computer system. The first question is registers. And next one, in order to improve the execution speed of a particular program, how mapping is done. That is, registers are used to store variables. Cache memory is used to store control loops. And main memory is used to store normal instructions. And secondary storage devices are used for normal instructions. And coming to the last topic of discussion. Okay, in this present, this one is hardware protection. For this topic, hardware protection. So first of all, what is hardware? You already know that every computer system is mainly collection of 3 components. Number one is CPU, second one is memory, and third one is IO device. Number one, first one, CPU, second one is memory, and third one is IO device. How CPU is protected from other processes? How CPU is protected from blocking of one process? Number two, memory. The basic principle is that whenever the user is trying to execute any particular program, first of all, a program should be copied into main memory. In main memory, where you are going to be copying your program? Where you are copying? Wherever the space is available, in that you need to copy it. And you please try to see that your program should not overlapping with any other program addresses. It should be protected. That implies whatever the area you have been occupied for running your program, it should be protected from other processes. How? Number three, IO device. Naturally, some IO devices can do only one operation at a time. Suppose if multiple people are trying to operate that IO device at the same time, how do you protect this IO device from another operation? This one. Let us take by means of a small examples. You're already aware that multiprogramming. What is multiprogramming? More than one program can be simultaneously reside in main memory. during the execution of one program, in case if any program requires an IO operation, then only CPU is switching from one process to another process. CPU switching is eligible only when IO operation is encountered. Remaining cases, it is not possible. That is the standard definition of multiprogramming. Now, suppose in a main memory, there are four programs are running. In one program, one guy has been written a program, a for loop. How did they written? For semicolon, bracket close, with and the immediate next statement is I is equal to 10. For bracket open, semicolon, there is no initialization, there is no condition, there is no increment, brackets are closed, and the next line is I is equal to 10. This loop is executed how many times? Infinite number of times. What did it execute? I is equal to 10, I is equal to 10, I is equal to 10. This line is executed infinite number of times. The value 10 is assigned to the memory location I. The value 10 is assigned to memory location I. This is continuously executed. It never stops. Now the CPU is continuously executing that program. Then what about the next three programs? They're simply waiting for the CPU. When the CPU comes to me, that implies your CPU execution is going to be completely dedicated to only one particular process. Your CPU execution is completely dedicated to one. How do you protect your CPU from this kind of wrong programs? That is the first problem. How can you protect your CPU from this kind of infinite structs? That's it. And second one, memory. So already you know that memory, whenever the user is trying to execute any particular program, first of all, a program should be copied into main memory. So you need to see that your program addresses should not be overlapped with another program addresses. And third one, let us take IO protection. What is this IO? Suppose you have a printer. The printer can be a non-shareable device. Non-shareable in the sense, it can be accessed by only one person at a time. If one person is already taking a printout, okay, if one person is already taking a printout, at the same time, if another person comes, is not eligible. Yes or no? Two persons cannot be do at the same time. So we need to block that particular operation until this particular job has been completed. Okay. Before going to the detailed discussion about this particular thing, we'll see. Whenever the user want to take any particular printout and a paper, first of all, whatever the content you want to take it, first of all, the content has to be copied into buffer. From the buffer, the values are going to be transferred to your printer device. So let us take a small example for this. Your buffer capacity is 100 lines. Your buffer is not protected. Let us assume your buffer is not protected. Your buffer capacity is 100 lines. Suppose process 1 prints issues a request for it as print 100 lines. Now the printing process is going on. After printing 50 lines, another process has been issued to print 100 lines. Then what happens is that the second process 100 lines is again overwritten on buffer or written on buffer. Why? Because I am already saying that buffer is not protected. That area is not protected. Then what happens? After seeing the printout, first 50 lines of the first guy, second 50 lines is of second guy. The total output is wrong. Then what you are going to do? The buffer has to be protected and IO has to be, printer has to be protected. How do you protect this? So that is why it is called as IO protection, CPU protection, and followed by memory protection. Now we are going to see IO protection. IO protection is done through dual mode operation. IO protection is done through dual mode operation. What is this dual mode operation? Your computer system operations has been defined as two modes. Your computer system operation has been defined as two modes. Your computer system operation has been defined as two modes. Number one is user mode. Number two is monitor mode. Number one is user mode. Number 2 is going to be called as monitor mode. In monitor mode, the CPU does not accept any commands or requests from the user. The CPU does not accept any kind of request from the user. The CPU does not accept any kind of request from the user. But whereas in the case of in monitor mode, in user mode, the CPU accepts commands from the user. So whenever the user has been switched on, first power on self test. At that case, it is in monitor mode. After that ROM BIOS, again it is in monitor mode. And booting process, again it is in monitor mode. Once the total booting process is done, then it enters into user mode. Now you have been typed one command. Now it is accept your command. Again, that is in user mode. Once a command is taken, again it is going to be entered into monitor mode and execute that command, and output is going to be displayed on the screen. Once the output is displayed on the screen, again it comes back to user mode. That implies your computer system is frequently switching from user mode to monitor mode and monitor mode to user mode. Your computer is completely switching from user mode to monitor mode and monitor mode to user mode. Now, now this concept is used for protecting your IO devices. How? How they have been used? All privileged instructions, whatever the commands which can be used for controlling the IO devices, they are all defined as privileged instructions. The commands are going to be defined as privileged instructions. In case you want to activate any kind of IO device, that must be done by using a privileged instruction. The privileged instructions are always executed in monitor mode only. The privileged instructions are always executed in monitor mode only. Is it clear, everyone? Now, so what happens is that initially, let us take an example. Initially, printer is in user mode. If process 1 issues a print request, immediately the printer IO device turned to monitor mode. Once it is turned in monitor mode, it does not accept any commands from the user. If a second person makes a print, simply it displays that printer is already busy, you are in the queue. That's enough, it's over. So once the first user is completed, then again it turns to user mode and takes the second request and go ahead. And at a time, the printer can be operated by only one person at a time, so that there is no mismatch at all. That's enough. That is going to be called as IO protection. That is going to be called as IO protection. And coming to the next very important one is that CPU protection. So just now I told that in case the processor is blocked by any one of the program instruction, how can you come out? If a processor is blocked by any one of the program, then using timer control, you can switch the CPU from one particular process to another process. So whenever the program has been started at execution, it starts, it estimates how much amount of time to run the program. So after stipulated amount of time, if the program is not properly completed, CPU operating system forcibly stopping the execution of that particular process and giving the control of the CPU to some other process. Once the timer control is done, okay, it becomes 0. The CPU control is automatically shifted from one process to another process. Using timer control, we can protect a CPU. And coming to the next one, memory protection. And third one is memory protection. So here everyone is already aware that whenever the user is trying to execute any particular program, first of all, the program should be copied into main memory. Whenever the user is trying to execute any particular program, first of all, the program should be copied into main memory. In main memory, where you need to copy the program, wherever the space is available, you please try to Okay, copy that area. How do you know that where the space is available and where the space is not available? The memory management system is responsible for keep track of which parts of the memory is full and which parts of the memory is empty, which parts of the memory is full and which parts of the memory is empty. Memory management system is responsible for keep track of which parts of the memory is full and which parts of the memory is empty. I mean, similarly, memory management system is also responsible for which process has to be loaded and not to be loaded, which process has to be loaded where. It is decided by memory management system itself. Okay, now how do you protect this? In memory management system, we have a memory allotment table is there. In that particular table, you have the entries like this: process ID number and base address followed by limit address. This one. Before going to why they have been divided like this, we'll see. You're already, in case you have a knowledge on computer organization, we have a concept of relocation. We have a concept of relocation. What do you mean by this relocation? Relocation is nothing but moving your program segments from one particular area to another area, which is going to be called as a relocation. Relocation is a process of moving your memory process segment from one particular area to another area. Why we need to move? Due to fragmentation problems. Due to fragmentation problems. What do you mean by fragmentation? Let us take an example. So we have one program running here and we have small space or 20 KB of space is available here. Another program is running here. Another 20 KB is running here. Another 20 KB space is available. Another program is running here. So there are two memory holes are available. One is on the top, that is 20 KB. Another one is on bottom, 20 KB. In between, there is a lot of processor running. Okay, total memory available is 40 KB. Now, whenever the user is, suppose user want to run another process which requires 40 KB of memory. Is it possible to run the program? No. Why? Because according to basic principle, whenever the user is trying to execute any particular program, first of all, a program should be copied into main memory. How much space is required? We require 40 KB. The 40 KB is available, but it is not continuously available. It is, okay, some 20 KB is available in upper side and some 20 KB is available in bottom side. I cannot copy some program here, some program here. I cannot able to do like this. So whatever the amount of memory which is going to be required to run your program, the memory should be in continuous fashion. Otherwise, the program cannot able to run it. Whatever the amount of memory which is going to be required to run your program, the memory should be in continuous fashion. Okay. Now, so here you have a 20 KB and here you have 20 KB. Okay. So this particular 20. So what you need to do is that in between whatever processes are running, these all processes are either moving towards up or down. This particular process is known as relocation. So relocation is a process of moving your program segments from one particular area to another area. So now we'll define one standard definition: external fragmentation. What is external fragmentation? Required amount of memory is available, which is not in a continuous fashion. Hence, the user cannot able to run the program. This kind of a process is known as external fragmentation. The required amount of memory is available, but it is not in a continuous fashion. Hence, the user cannot able to run the program. That is external fragmentation. Similarly, we have internal fragmentation also. It is the smallest memory hole which cannot be accommodated for running any one of the waiting process, which is called as internal fragmentation. We will going to discuss such kind of a topics in detail in memory management schemes. Now, in order to overcome this internal fragmentation, we use compaction. Compaction in the sense moving your memory segments either towards up or down. Moving your memory segments either towards up or down. So while moving, this process is called it as relocation. But very careful that while relocating your program, we have do two things. Number one, we need to copy all the instructions from this place to that place. Number two, you need to change the address of each and every instruction. You need to change the address of each and every instruction. Copy is a compulsory activity. No one can eliminate it. But the most of the processing time is wasting for changing the address of each and every instruction. Most of the processing time is wasting for changing the address of each and every instruction. Let us take an example. If a program is copied in some area, 10,001, 10,002, so on up to 10,150. The program size is 150. Let us take. Now, your program is now located in 10,001 to 10,150. Due to fragmentation problems, now your program is moving from 10,001 to 20,001 to 20,150. Then what you need to do? First of all, you need to copy all the instructions from this place to this place. Number two, earlier address of instruction is 10,001. Now you need to change it as 20,001. Earlier you have 10,002. Now you need to change it as 20,002. So on up to 10,150 has to be now changed to 10,001, 20,150. There is copy is a compulsory activity. No one can eliminate it, but the most of the processing time is going to be wasting for changing the address of each and every instruction. Then, in order to overcome this particular problem, in order to improve the speed of an execution, the address has been split into two parts. Number one, base, and second one is offset. The address has been base plus offset. These topics are already done in computer organization. Again, for your purpose, I am telling this one again. Okay, now we'll give an offset 1, 2, so on up to 150, and base value is 10,000. Base value is 10,000. Base value is 10,000, and base value is 10,000. Okay, 10,000 plus 1, 10,001, 10,000 plus 2, 10,002, 10,000 plus 150, 10,150. Sir, why we need to divide the address into two parts? If the program is relocated from this place to this place, then you don't need to change each and every instruction address. Same address, 1 to 150, same you can give as it is. But instead of the base value 10,000, you need to change it as 20,000. Now 20,000 plus 1, 20,000, 20,000 plus 2, 20,002, 20,000 plus 150, 20,150. The relocation is possible simply by changing the content of base register. This is one bit we already got. How relocation is possible while getting an external fragmentation concept. It can be done by changing the content of base register. The relocation is possible simply by changing the content of base register. Now, coming to the next very important one is that, okay, now the address has been split into two parts. Number one is base, and second one is going to be called as limit value. First one is base, and second one is going to be called as limit value. Now, so now this seems, now we can see this memory allotment table. In memory allotment table, we have three columns. First column showing that process ID number, and second column is showing that what is the base address, and third column says that limit value. Coming to the first one, process ID. So there is multiple processors running your computer system. Each and every process is going to be identified by your operating system by using process ID number. By using process ID number. Okay. Next one. So second column, base address. What is it? Base value. What is the maximum capacity of your program? Is called as a limit value. Now let us see. Okay. Process number 1020. It is copied in the starting address is 2000. It occupies the maximum space 400. That implies P1020 process is running in the area of 2000 to 2399. And the process P1020 occupies the memory space in between 2000 to 2399. Similarly, process 5050 starting address is 2600. It occupies 200 value. That limit value is 200. That implies it occupies the space 2600 to 2799. Is it clear, everyone? That's now. And this is how the memory allotment is going to be done. Whenever a new process is entered into memory, before entering into memory, whatever the address which has been specified, it simply checks that whether the address value is lies between these two. If it is not lies between these two, yes, it is a safest address. It is lies between these two. Sorry, overlapping is possible. Immediately the request is rejected. That implies, let us take an example. Okay, suppose process 6060. The starting address is specified as 2700. 2700 is lies between these two. This is 2000 to 2399. No, it is not lies between. This process address is 2600 to 2799. But process 6060 address is 2700. It is not eligible. Why? Because the address is already occupied by 5050. Immediately the request is rejected. That's it. Now, this is first kind of restrictive. And a second one, while executing one process, whatever the addresses generated by that particular processor, you please try to see that that addresses is only referring the process related area only. Process 1020 must be referring an instructions between 2000 to 2399, not more than that. So whatever the addresses which has been generated while executing process P1020, the addresses must be always between 2000 to 2399. That's it. So that's why I have been shown in this particular table the memory protection, how it is done, and that is done by using base and limit value. Now CPU generates a logical address. So whatever the address which has been generated, that address must be always, that address must be always greater than or equal to base. That address value always greater than or equal to base value. And after that, in case it is not greater than or equal to base value, immediately you have to give an interrupt. You are trying to access an illegal address, addressing error. In case it is greater than or equal to base error, in order to get an effective address, this is call it as addressing mode. The addressing mode simply specifies the way of evaluating the operand part of an instruction. So content of base register plus offset, that is the limit value. So whatever the address you have been generated, that value should be greater than or equal to base, and that value must be less than 2400. There is, suppose if you are executing P1020, okay, the address must be greater than or equal to 2000, must be less than 2400. Then only it is a legal address you are executing process P1020. Okay, otherwise you are simply says that it is trapped to an operating system. Okay, monitor addressing error. This is memory protection. So memory protection is done by using base comma a limit register. Base comma a limit register. This is. Now, how do you get a question in gate? So in gate, how do you get a question? So we have matching question we have been got. Number one, CPU protection. Number two, memory protection. Number three, IO protection. On the right hand side, we have three options. Number one, timer control. B, using base comma limit register. C, dual mode operation. So one is matched with CPU protection is done through timer control. Memory protection is done through base comma limit register, and IO protection is done through dual mode operation. IO protection is going to be done through dual mode operation. That's it. This is end of your second topic of discussion. Now we'll see small what we have been gone through so far this 2 hours of discussion. So what is a computer system? What are the different peripherals are there in your computer system? How they are going to be connected with each and every other? How they are going to be connected each and every other? And whenever the user has been switch on a computer system, what are the various actions which is going to be done by your computer system? And followed by, we have been seeing a broad topic of interrupts. Already I have been defined what is an interrupt. An interrupt is a signal which is received by the microprocessor indicating that one external IO device want to communicate with the CPU, and followed by the modes of data transfer between CPU, memory and IO devices. The modes of data transfer is happened by using three methods: program control data transfer, interrupt initiate data transfer, DMA transfer. So under this particular three methods of data transfer, okay, which method of data transfer is 100% eliminates the participation of the processor is DMA. Already I have been told that we have got some questions. Scanf percentage the ampersand A, which is what kind of operations initiated by your CPU in the sense IO read followed by memory read. For printf, memory read followed by IO read. This is what we have been seeing, and followed by we have been seeing about storage hierarchy. So whenever the user is trying to execute any particular program, so your program is not only copied into main memory, your program is going to be distributed among all these particular memories and try to see that your program is working more faster. That's why it is call it as memory hierarchy, or may call it as goal of memory hierarchy. The main goal of memory hierarchy is that we have to achieve a highest possible average access speed while minimizing the total cost of the memory system, and followed by caching, coherency, and consistency. That implies whenever a value has been shared by multiple processes at the same time, if you are not using any proper security mechanism for the data will going to be enters into inconsistent state. Okay, in order to overcome such one, we will use coherency and consistency methods. And followed by the last topic of discussion is hardware protection. The CPU hardware in the sense your computer system is basically it is a collection of three components. Whatever number one is CPU, second one is memory, and third one is IO. The CPU protection is done through timer control, and IO protection is done through memory. So IO protection is done through dual mode operation, and memory protection is done by using base comma limit register. Base comma limit register. That's it. This is topic why I have been. So and coming to the end of this session, tomorrow what we're going to see is that computer system structures is done. Now we are entering into pure operating system structures. So what we're going to see tomorrow is that whenever the user is trying to invent any operating system, what are operating system is nothing but from the previous class definition you already know that it is a collection of system programs. Whenever the user is trying to invent any operating system, whenever the user is invent any whenever the user is trying to invent any operating system, what are the various factors he has to be considered? What are the different programs he has to be write? What are the different programs he has to be write? What are the different programs he has to be write? And how this particular interface is make available to all users. Here's one. This is what is operating system structure. Simply says that what is an operating system? What are the various components of an operating system? What is the various components of an operating system? Whenever the user is trying to execute invent any operating system, what are the various programs he has to be write? And how this interface is makes available to the user. How this interface makes available to the user to conveniently use this particular one. We're going to be see tomorrow. Okay, and thank you one and all. Can any team people can come? Yeah, the session is over. Yeah, yeah. Can I winding it? Then I close it. Yeah, sir. Thank you.